Well, good morning, everybody, and welcome to Ellensburg, Washington, USA. This is a live stream from the auditorium in Central Washington University's Discovery Hall. Scott and Garrett, thank you for the report on 5x5. I'm glad that you can hear me. You're looking at a title slide, Volcano Science and Eruption Response as a USGS Hawaiian Volcano Observatory scientist. Special guest here, all the way from the Big Island of Hawaii, Heather Winslow. So glad you could join us here. Let me get you on camera. Let me get myself on camera and we can talk a little bit. There's the crowd today. People filtering in. We haven't had one of these talks since early June. Hi everybody, how are you doing today? Thank you for joining us for this live program, and if you're watching this in recorded form after the replay, I'm a little amped. There's a bunch of new whistles here. If you're watching this in replay, you can scrub ahead 12 minutes to the beginning of the program. But this is live, and for the next 12 minutes, we'll just be saying hi to everybody. Where are you viewing from today? Can I say hi to a number of you, and then we'll swing you around and give you a chance. We've got some new faces and some old faces, some graduate students, some undergraduates. There's a buzz in the room for our first talk of the school year. Everett, Washington, Portland, Oregon. Vera is in the United Kingdom. Good evening to you. Friday Harbor, Washington. Snarky user is actually here in the room. All right, Snarky. Fabian, Alberta. Kirk is in Sweden. Bernadette is in Marysville, Virginia. Salem, Oregon. Garrett, the Dutch night owl from the Netherlands. Norley's back. Norley is back. Ellensdale, Minnesota. Brian Finch. Brian and his lovely wife were here from Worcester, UK. Brian, looks like you made it back home safely. It was a pleasure to meet both of you and visit a little bit in my office. Lodgepole, Alberta. Burpengary, Australia. Hello, Graham. Charles is on vacation in Las Vegas. Kettle Falls, Washington. Jocelyn's in Quebec. Tom is in Arnhem, Netherlands. Tom says the video is pretty bad. Can you all report? Are we 5x5? Is it just Tom's problem? Can you get me a drink of water, please? Thank you, Chris. Margaret is in the Netherlands. Vienna, Austria, Chelmsford, England. I'm just kind of waiting to see if it's just Tom's problem or if everybody's noticing a major problem with video here. Thank you, young man. Thank you, Chris. Looks like it's 5x5. Okay, Tom, refresh your whatever. Okay, looks like we're doing okay. Just letting you know, it's going to make me feel better to say this to you. I'm using new microphones set up by Nat the Wonder Boy, and I'm going to turn on this speaker so that our speaker can be projected into the room. And if all goes well, the audio that you hear will not be any different than you'd hear right now. Tom is the problem. Okay, don't take it personally, Tom. All right, great. Okay, let's swing you around and have you enjoy the room, and we'll begin at the top of the hour. Thank you. Haven't seen you yet this quarter. How are you?
Good, how are you?
Doing fine. We'll visit sometime. Saw you this morning. Hello, how are you?
Good, how are you?
Good to see you again. Ryan?
How's it going?
Good, man. Bunch of faces I haven't seen. Dakota, I guess I've seen you already a little bit. Great. Forgot your name.
Jackson.
Jackson, that's right. Yeah, good to see you. I'm doing fine.
It's a little colder than usual.
Yeah, I guess it is, yeah. You here for fun or for class?
For class.
Okay. Well, hope you enjoy it.
Yeah, no, excited.
Do you know Jess?
No.
Jess, this is Jackson.
How was that job?
How's it going?
Good,
Doing fine.
Hi, Nick.
Hi.
Probably we need to announce these again.
Okay.
I think a few came in without signing, but
Okay, I'll do that.
I'll say something and check with me on the way out to make sure I got everybody.
Okay, good. I can do that. Hey,
how are you?
good. You?
Good.
Have you been here for the last couple of weeks? I just haven't seen you?
No, I just came like on September 24th.
Okay.
Yeah.
Where were you in Germany this summer?
Yeah. And you know what happened?
Oh my gosh. Congratulations.
Thanks.
That's so nice.
He's gonna be here like on October 25th.
Good. Well, good. I want to make sure to meet him, okay?
Yep.
Great. Is he a pole vaulter?
Yep.
Okay.
What do I do next?
Yeah.
Now we can tell the tea.
Yeah. There we go.
Okay, so that's a hot mic right now.
Hot mic.
So you guys can continue to chat, and I'm going to hear.
Clean.
I'm going to see if the whole. Well, yeah, get into the really good stuff.
Yeah.
You've
So
been
anyway,
saving
what
that.
I heard
Yes.
about Nick.
Oh my God, did you hear that? That's already out. You didn't tell her that, did you?
Promise.
Viewers,
but
can you
that's so
can
good.
you
That's so
hear
good to
not
hear
only
how
me
she's
now,
doing
but
and
can you
stuff.
hear our
Yeah.
speaker Heather? Could you type Heather
This is
5 by
like my
5,
first,
please,
real.
or speaker 5 by
Yeah,
5?
I've done some, and I was like going around and meeting with students. Yeah, I've done some remote stuff, and I was like, oh, this is like.
Awesome experience, but so exhausting.
It is, but it was so
Leave in
cool
the
because, like, I don't
comments.
know, in grad school, so many speakers came through, and you sign up to meet with them and stuff. Yeah, and I was like,
Carey.
oh, this is so cool to be kind of on this other side.
Okay, good.
And like be at a different university and like see your lab facilities and like what you guys are doing here, and so
Well, I
that was
think
super
Heather
cool.
is a
So, yeah,
loudspeaker.
thank you.
After this, I'll show you and the lab.
Oh, yeah, I wanna see your
experience,
lab.
And then we'll just chill, like
Yeah.
get a snack or
Yeah.
Thank you,
Because
thank you,
that
everybody. I'm glad you can hear Heather.
Yeah.
get something light or whatever you want.
Yeah.
We'll just sit.
Easy. Yeah. Oh yeah, and I do want to see your lab because that's what Marie did not take me to that 'cause she was like, Hannah will show you this. Yeah.
I mean, it's very small, so.
Okay, they can hear you.
Oh,
Doing
perfect.
well. Yes. You just
Can they hear
can't-
this one
I'm sure they
from
can. They
just
know,
reverber?
They know
Yeah,
that voice.
they know. They know.
No, they don't.
Is this? Do you guys do this every week, all semester?
Every
Is
other
it
week.
Every other. Okay. Nice. So
Like 5
cool.
a quarter.
Yeah.
Because the quarters are so short.
Oh,
Like
that's
10
right.
weeks.
So quick. So quick. Yeah.
Couple final things.
Mm-hmm.
I'm going to start at noon. I'm going to say a few things to everybody, talk about speakers for the rest of the quarter, turn it over to Hannah. She's going to introduce you after yawning, and maybe while yawning, and then it will go directly to you.
Okay.
And occasionally you'll look up there and you'll see this instead of your slide, because this is what's being broadcast out to the YouTube crowd. So all I'm saying is if you see that, just give me a second. I'll get to the
Okay,
slide.
yeah.
I know you need
So
it.
anyway, like
Right.
yeah.
Like for instance, right at the start, I'm going to be like doing a shot of you so they can see you. And if you're like, anyway, my first slide, and you're like, oh my God, that's me. It'll just be for just
Yeah.
a quick second, and then
Yeah.
I'll get to your slides.
It's hanging out. Everything's good. Yeah.
We'll do some live Q&A. Are you okay with that?
Yeah.
Okay.
Yeah.
Good.
Answer as best I can.
Yep,
So
that's
we will.
right.
Yeah.
Same.
Yeah. That sounds good.
This will be great.
And
Thank you.
if they ask questions, like, is it like everyone can hear online, or are those questions need to be repeated?
Good question. I'll be prompting you to repeat the question
Okay,
so that
okay.
people at home can hear it. Yeah, very bright.
Yeah. Cool. Nice.
And Hannah has refused to do any introductions of any of the speakers,
Honored. Yeah.
and so this is it.
It's true, you are the first. Didn't do Kelly, didn't do Marie, didn't do anyone.
Did you Kelly? Stage fright.
She tried to pawn it off just a second ago. She's like, it's all written
She was
out.
like,
You just
actually,
always-
Heather's the
It
worst.
is,
Can
it
I
is
get
weird.
it?
Like, my job is public speaking, right?
Yeah.
But for some reason,
The camera.
yeah.
It's scary.
It's like it's this thing, and I don't.
Yeah.
Who am I to be like, hello, everyone? But yeah, so
No,
you're the
it's-
first. Honored, like, hello.
Yeah, it's me. No, I'm honored. Thank you, Hannah.
He's freaking out.
It's like my hand. Look at me. Look at me. Yeah. Man. Now they know. I was I was like, well, if I'm easy, but you can take notes. I was randomly on a video podcast like 2 weeks ago on
so
YouTube, like not told in advance. And I was.
What do you mean not told me? It's like,
They were in the lab doing like a session with another professor, and I was doing a lab training for the undergrads, and they had mentioned there might be a podcast crew in the background. And I came like from Eruption Response, like sin Eruption. I was still in field gear, all grungy, and was like, okay, I'm gonna help with the undergrads do this thing, and then I'm gonna go do lab stuff. And then they had like a video camera, and they interviewed, and I was like, I was like, I'm so awkward. Yeah. You like post that up actually.
All right, we're gonna- Okay, hi everybody. We're about to start, but this is a brand new setup that we have. So in addition to the normal thing where the speaker is talking into a microphone that's going directly to YouTube, we're going to do a new thing, which is get this speaker to fire up and have Heather's voice not only go to YouTube, but also go to the room. So it hasn't happened yet, but I'm going to try it right now, okay? So I'm going to talk to myself as I do this.
Yeah.
And if you come up to talk to Heather afterwards, I'm Bandana Boy. I got bandanas all over here, there's a tripping hazard on this cord, okay? Just letting you know. Watch your step if you come up here. So watch me operate here. This is great. This is an older gentleman talking to himself. He's plugging into the Rode jack.
Moment of truth.
You can feel the tension in the room. Now we're going to turn on the speaker. I've been trained by Nat Nickel, the Wonder Boy, whose office is right down across the way in Samuelson. He is a wizard, and he can support anybody who wants to teach with advanced AV setups on campus. Nat Nickel. Power is on. And now
Sounds the same.
I'm speaking.
Oh.
Oh, hello.
Wow.
Oh, hi. Heather, do you have something to say real quick? How was your trip over here?
It was great. Oh, I hear it.
Yeah. Okay.
It's working, I
yeah.
think.
Okay. Everybody can hear Heather okay as well? All right, great. Wonderful. Kind of a funky way to start, but I have your attention now. Thanks. Let me do a couple quick things. Now that it seems like we're functional with everybody, including the home crowd, I assume. Welcome, everybody. This is the first of many Friday at noon talks for this school year. This is the first one. We didn't have one last Friday. And if you haven't heard the schedule yet, we have a few more lined up. I'm about to read them to you. But before I forget, Bree McGinnis is waving her hand right now. She's the department chair, and she wants to make sure we are legit. So we are doing this for YouTube, and occasionally the camera swings around and shows this half of the room, this diagonal half of the room. So if you're on this side, that means you're okay to be on camera, and you give permission to be on camera, and there's paperwork outside the door. You need to see Bree on your way out if you haven't done that already. And you guys are in the shadow zone. You're never on camera, and I promise I won't put you on camera, but you're signing a different form. Is that true? So everybody's signing some kind of permission form with Bree McGinnis, and if you haven't done it on the way in, please have Bree flag you down on the way out, and we can do that. That's Audrey Huerta, who's got her hand up. She's teaching 304-504 this quarter, so that's a class where you need to sign in with her. So if she doesn't know many of you, so if you haven't connected with Audrey yet, please check in with your instructor, Audrey, if you're Geology 304 or 504 for this quarter only. Okay? Hey, there's a new setup with the snacks and everything. Special thanks to Jess and Yusei and a few others that set that up. No Vinmans this year.
Let the pause settle.
Thank you. Most of you know Hannah Shamlu, geology professor here. So Hannah and I put this schedule together. And the schedule is, after today's talk, next Friday, come on back, Friday, October 11th, Luciano Marchetto will be talking about hydrology in the humanitarian sector, Bangladesh, Yemen, and Brazil. So a hydro talk next Friday. The following Friday, we're going 3 Fridays in a row. In other words, two Fridays from today. Angie Diefenbach, former student here, October 18th. She works for the Cascade Volcano Observatory. Angie will be here giving a talk, the 2018 Kilauea Eruption and Beyond, using drones to monitor volcanoes. We're very proud of Angie, and I'm sure you'll enjoy that talk. Then we take a Friday off. Then Jeff Tepper, University of Puget Sound, is here on November 1st talking about the initiation of the Cascade Volcanic Arc. And finally, then Veterans Day weekend, then our final talk of the fall, November 15th, Andrea Spolar, Understanding the Impact of Arctic Amplification through Svalbard's Snow and Ice. So Professor Susan Kaspari has a number of postdocs and other visiting scientists, and so we'll have 2 of those folks involved this fall. He pauses to wonder if there's anything else to say. I don't think so. Hannah will be introducing our speaker using this microphone. She's going to hand the mic back to me.
Testing.
And away we
Testing.
go for our speaker. Hannah.
All right, hi everyone. It is my great pleasure to introduce Dr. Heather Winslow, petrologist and volcanologist. Heather and I met in 2019 at a summer program called CIDER, which was focused on modern questions in volcanology. So we literally spent 4 weeks doing nothing but eating cafeteria food at Berkeley dorms and thinking about volcanoes, and it was a blast. So very grateful for that experience. Heather has a very impressive background. So she completed her BA in environmental science at a small liberal arts college at Willamette University in Oregon. Then she did a post-baccalaureate at Oregon State University working in the Argonne Geochronology Lab. Then she liked this geology thing so much, she went on to do a master's and a PhD at University of Nevada, Reno with Philip Ruprecht. And she was working on volcanoes in the southern Andes, specifically Corancaye in Chile, which maybe she'll mention today. Then, we're not done yet, then she did a research internship at USGS Cascades Volcano Observatory, only 4 hours from here in Vancouver, Washington. Now, Heather is a Mendenhall postdoc fellow. So just for some context, Mendenhall postdoc fellowships are very prestigious, and Heather has one at Hawaiian Volcano Observatory. So she's going to walk you through some of her history as a geologist and tell us a little bit about the work she does. So please join me in welcoming Heather.
Awesome. Okay, everyone can hear me still well with this? Okay, great. Thank you so much for having me. I'm really excited to be here and talk to your department. Thank you to all the students who came the hour before. We got to chat kind of career paths and options. And so it was great to kind of have that connection with you all. As Hannah mentioned, I am a postdoc fellow at HVO, so the Hawaiian Volcano Observatory. I started just this January, so I've been there just under a year. But it's about a 2 to 3 year contract. I'm really excited about the projects that I'm working on there. But today's focus of the talk is less research focused and is a bit more about what a day in the life looks like at HVO and also what eruption response is. What are the roles of HVO and other volcano observatories and the kind of the interplay between research and also monitoring and like our services to the community. So I obviously love talking about science and research, and if you have more questions about that later, happy to talk about it, or if there's time, I have a few slides because I couldn't resist. And so to get started here, this background photo is from the most recent eruption at Kilauea that happened just a few weeks ago from September 15th to the 20th in the Kilauea Middle East Rift Zone. And so this is, it started to open up within the crater of this area. This is within the Pau crater, and we had some reactivated fissures. These are maybe about 10 meters high, so about maybe 30 feet-ish. And this was a cool eruption. It was my first eruption that I got to experience that was prolonged enough to have some more eruption response since working there. And I'm going to kind of take you through what that week looked like. But before getting into those details, just to give you context of what I study and what I'm excited about and how I got into volcanoes, I was always fascinated by looking at micron scale chemistry and changes that have really large impacts and large conclusions about a volcano. I was always fascinated by them. And I actually didn't major in geology, but I just got pulled in that direction. And so that's always kind of been this driving force for me. And it stayed with me in how I research. So I'm an igneous petrologist, and I'm really excited about crystals and minerals and using mineral scale techniques. And that is because these crystal records inform us of pre-eruptive conditions. And so as a crystal grows in a magma chamber, you are getting, it's continuing to grow and trap the surrounding environmental conditions. You get to see what it went through before it erupted, and we get to probe into that to see what was happening prior to an eruption. And I think that information is really useful, and it's exciting to look into, and we have tools to do so. And with that, we can answer questions about like how hot was the magma prior to eruption? How deep was it? Where was it stored? Are there multiple storage regions, and are they interconnected? How is this happening? Did the magma interact with other magmas? Did it interact with wall rock, with gases, with a hydrothermal system? What was happening before this eruption and maybe potentially triggering an eruption? And then finally, how long has the magma been there? Thinking about time scales. How quickly did it erupt and come to the surface? How long has it been hot? And how long has it been maybe potentially solid? Did it quickly come to the surface and melt and erupt? All of these questions are things that what guide my research and have kind of guided my path for what I was interested in. And so this is the framework of how I take in geology and how I take in these systems. And what I like to look at is like the textures, the zoning, and the geochemistry. And pretty much you can get these rocks looking at this mineral scale, and it informs you of this type of architecture and this type of plumbing system. And so as a real life example of some of the work that I've done, oh, real quick as a side note here, as I'm an igneous petrologist, and I'm biased, I think that's the best. But the great thing about geology is that it's so interdisciplinary, and there are a lot of other different topics that help us understand a more well-rounded understanding of the volcano and an eruption. And so we compare this with other geophysical data sets, thinking about seismicity or deformation. Are we seeing inflation prior to the eruption just as the diffusion chronometry is also showing recharge? What's going on there? Are we looking at the gas data? And all of these data sets combined give us a much better, well-rounded view of what's going on underneath the surface that can help monitor and think about future pre-eruptive unrest, but also can guide us in really interesting research questions. And so a real life example here is this is a rock that I've been now using on a couple slides now for my PhD. This is from the Southern Andes in Cordon Cauye. It is a mafic enclave hosted within a rhyolitic glass. So it's this really interesting interplay here between basalt and rhyolite. And this is a petrographic image. It was a very crystal-rich rock. And here are some of those zonings, those textures that we're looking at the mineral scale. Taking that into a lab and getting on a microprobe here is where we could get some of those chemical compositions. And not just point and IDs, not just seeing the base chemistry, but actually looking at the, I'm going to now use the stick here, looking at the distribution between crystal phases and other crystals or between melts. And looking at the distribution of that chemistry across a grain can give us really important information. And in this case, I was looking at, this is a plagioclase grain touching a clinopyroxene grain. And I was looking at the partitioning of magnesium between those. And the reason for that is that it was temperature dependent, how it moved across the crystal lattice. And because of that, we could get storage temperatures and use it as a thermometer. So thinking about this crystal-rich mush underneath the volcano, how hot was it being stored? But further than that, and so we were able to get a storage temperature, but further than that, the shape of this profile and the distribution of that can also be used as a cooling rate. So now not only do we have a starting temperature, but we're able to think about how quickly did it cool and what process does that represent. And in this case, we did some diffusion chronometry, looking at the magnesium and plage here, and was able to look at, on the order of, depending on which diffusivity you're using, a few years to a few decades, which means this was no longer a syn-eruptive process we were looking at, it was pre-eruptive. And this was super helpful in some of the final conclusions of my PhD. And so I'm not getting into the huge details of what that research actually is, but thinking about how we're using these data sets and what questions they can answer. So now getting into a bit more of my current job and where I'm at the Hawaiian Volcano Observatory on the Big Island of Hawaii in Hilo. The Hawaiian Volcano Observatory was established in 1912, and there are 4 other observatories in the U.S., and that's the Alaskan Volcano Observatory, the Cascades, Yellowstone, and California. The Cascades Volcano Observatory was established in 1980, just after the Mount St. Helens eruption. I think there's really a big impetus there to see that we needed one. Unofficially, between universities and other workers, there was kind of already that established, but it became a bit more official after the Mount St. Helens eruption. And all of these different observatories have slightly different roles because they're in slightly different volcanic environments. So while we are all under the same umbrella of volcano observatories in the US, we all kind of have different goals at each observatory and different techniques and methods that we're using to study the volcanoes. So getting into specifically HVO, we monitor the Hawaiian Islands here, the Big Islands. There are 5 volcanoes above the surface here. Kohala and Mauna Kea are less active and considered more closed there. And then we have Hualalai, Mauna Loa, and Kilauea. And then also Loihi is a seamount, but actually has been recently renamed to Kamaehua Kanaloa. And so part of our monitoring is covering all these volcanoes, as well as the island of Maui and Haleakala. Our goal and our job at USGS is to monitor the Hawaiian volcanoes and earthquakes along with the volcanoes in American Samoa, and then assess the volcanic and seismic hazards, and then research such activity. And then the final bit of this is informing the public and safety officials. So this is where there's that interplay of it's not just research, but we're also monitoring and working with hazards. And at each observatory, oh, it's hard to see that, perfect. At each observatory, there's petrologists, seismologists, gas geochemists, deformation, there's GIS and mapping, field work, instrument crews, and also science communication. There's a lot going on at an observatory to really have this well-rounded view, and a lot of different places you can fit in. So thinking about where our building is and what we're doing, if we zoom into Kilauea, this is where our office used to be, or I guess maybe I'll use this. Oh, there it. Oh, it is a little. It's a little lag, but okay. So this is where HVO building used to be, and right now we're looking kind of south across Kilauea crater and across the summit here to. There we go. This is the Kilauea Visitor Center. So if you drive into the park, this is one of the first things you'll see. Kilauea Iki is up here. There's this actual crater rim drive that circles the entire summit here. And this highlighted yellow, you can kind of see some lines. This is where the parking lot and this other side of the crater rim drive was back in 2016. Obviously, a large event happened shortly thereafter, and that parking lot and road is no longer accessible, and a lot of it has fallen into the summit, and so this is now a closed road and a closed portion. But also, if we flip back and forth, this the summit edges, the crater edges here, also got a lot closer to HVO's building. So it no longer became safe. There was some structural damage. I think there was also some even prior to 2018 and 2004 to 2008 period. But officially after 2018, we could no longer be in that building, which was definitely a sad realization because it was a really cool office to be able to sit and look at Kilauea while you're messing with data about these Hawaiian volcanoes. It's a very special place, but is now no longer in use and is being reconstructed back to kind of prior to building. And so if we go on a little bit further, 2020, and during some eruptions, this is what the inside of the summit might look like. And we have different drop-down blocks after 2018 within the caldera. And then this is where it is today in 2024. And so this building is being reconstructed, and we are no longer here, but we are actually now based in Hilo. So we're in downtown Hilo in a temporary building space. And so HVO is on the bayfront, on the water, and it's very close to the University of Hawaii Hilo. This is really exciting because we actually have a cooperative agreement between the university and HVO. We share lab facilities, we have some funding that's there, and it was established in 1998. But in about 2012 was really when a lot of the eruption response and real-time chemistry during an eruption started to get going. Way before I was there, and I didn't help with any of this, but I have now been able to watch it in action. It's a very useful thing to have in an observatory. It's very cool. It's great to share lab facilities, and also this is great for the undergrads that are at UHH. They get to have opportunities to volunteer with our research and help us process samples. Even sometimes during an eruption, they can be in the lab and helping, just depending on a couple different factors. But it's a great opportunity for the undergrads to get that exposure. And so I just want to give a quick little overview of the facilities that we have between all of our shared lab spaces. We have some new investments that's been happening at HVO, but for our sample prep, we can do rock powdering and sample polishing, as well as we have some new microscopes and FTIR. And then we also have a physical volcanology lab, which is great for eruption monitoring, thinking about grain size of explosive deposits. So grain size, density, and then 3D scanners and printers. And then within our physical volcanology lab, we have a tephra lab. I saw you guys also have some of these. We have a cam sizer. They are non-destructive and can measure grain size and shape and distribution of those grains. This is that playing? Perfect. Okay. So as you send through some of these deposits, it'll come down and take images and give you a distribution of the size and shape, which can really help us understand insights for eruption dynamics, explosivity, and progression of the eruption. In real time, we can quickly get these analyses while it's going on. And then even the shape, eventually you do componentry on these, seeing how much of this eruption was juvenile. Juvenile meaning how much of it was actually liquid magma there being a part of this eruption as opposed to maybe just ripped off wall rock versus lithics. And then it can be more accurate than traditional hand sieving methods. And then the great part about this pairing with UHH is that our SEM is on UHH's campus. And so we're able to have a collecting instrument there that we can use. And this was with a supplemental grant recently. And so we have the SEM, but we were able to get a WDS detector on top of it. So you guys somewhat familiar with an SEM at all here? Yeah, lots of nods. Good. Okay, so scanning electron microscope. But the wavelength dispersive spectrometer is actually an add-on that microprobes have. So this gives us an added benefit of getting really high quality quantitative measurements quickly without having to send the samples to a microprobe lab. And so we can get quantitative precise compositions on glasses and on mineral phases within 24 hours of an eruption. And if we think about prolonged eruptions, seeing the change in chemistry is very important to understand where the eruption is going. So what does this look like? We have an eruption, we collect a sample in the field. What happens next? So this sample here is a water quenched sample, meaning this was molten lava collected and we quenched it. And we collected this in the field, and here is a video. That sample was from this most recent eruption. It was actually this exact sample that's being quenched in this video that will play following up. And I want to make a quick note here. So this is one of my colleagues. She is going in and collecting some of this. And so this is now molten lava that just was recently erupting. And we dump it into a bucket of water and then pour water on top of it to quench. And everyone's in proper safety gear. It is very hot to be this close to these lava flows. But the purpose of this is because we want to preserve the initial compositions and initial textures of this lava flow like during the eruption, as opposed to if the lava continues to cool slowly and flow, it's going to continue to evolve and not necessarily trap those pre-eruptive compositions. I'll play it one more time. potentially. There we go. And so the reason for this is that it really helps us preserve that initial chemistry. If we don't have explosive tephra coming out that we can safely sample, this is our next best option to get that type of rock sample. Something I do want to note while we're watching this too is, as HVO scientists here and working on Hawaiian Islands, we are trying to be very sensitive of the Hawaiian culture, and we are only sampling what's needed for our research and not trying to oversample, and trying to make sure that we do this in a respectful way prior to going out. And so, and all of these samples that we're collecting are then being used not just for research, but for continued monitoring. So there is that conversation, because in the Hawaiian culture, the lava is Pele, and this is a very respected, sacred thing. Okay, so we collect a sample, and now what do we do with it in the lab? Well, it first needs to dry. We just doused it in water. We can't just immediately start collecting data on it. So that is honestly one of the largest time-limiting factors at HVO, is just drying the sample after you collect it. And then we send splits out to our collaborators, because all of us are, during an eruption, are doing a lot of different things. You're in field shifts, you're processing data, you're collecting lab samples. We can't always be doing everything, and it's really helpful that we have these mainland collaborators that we send samples to help us out with some of that monitoring. In fact, one of the ways we do this is through fluid inclusion barometry. And so I can get into that a little bit later, but inside rocks, as it's trapping, as it's crystallizing crystals, you can trap little bubbles that are pressure capsules, and you can get the initial pressure and depth that this magma was coming from. But fluid inclusion barometry is recently new, and you can get these results within 24 hours of an eruption. So we can know if this is coming from shallow or depth, or which part of the chamber while it is still erupting. This is very important and very exciting that we can do this. Sometimes thin sections are made depending on what type of sample we're looking at, but one of the biggest things that we're looking at is EDXRF, so bulk chemistry. And to do that, we need to powder crush samples, and this is that upper right photo here, taking some of this sample and crushing it to a very fine powder, and then putting it in the EDXRF, which is the energy dispersive X-ray fluorescence. This gives us a homogenized pellet, which is in my hand here. It's sent under a hydraulic press, so it becomes a solidified pellet, and we put it in the EDXRF and get this bulk chemistry right away. And this is great because Kilauea is so well studied. We can compare that to a lot of eruptions in the past. There's a lot of comparable data sets that we can think about. Where was it coming from? Is this a new injection of mantle-derived magma and this eruption is going to be going for a while? Or is it evolved and kind of a colder stored thing that's coming out as like a little plug? This is super important information. And then we also do a hand crushing, sieve, and picking and looking for the mineral grains, both glass grains as well as the crystals, to kind of get at a lot of the things I was talking about at the beginning of this talk, thinking about their chemistries, where they're being stored, and diffusion chronometry, and just getting the mineral and glass chemistry. And this is then taken to an SEM or sent to the probe with our Calvio collaborators there, and we can send them data sets. But thinking about picking through grains, this is a really big benefit of Hawaii, is that a lot of them are olivine rich, and they are really big olivines. I don't know if you've worked much with it, but I had never seen such beautifully formed olivine before going to Hawaii. And so this was an entire picked glass straw here, and it's all olivine. And if we zoom in on some of these, you can see the beautiful crystal shapes here. This was incredible. And there's a new method where, if you guys are familiar with diffusion chronometry, in olivine, how those elements partition throughout can give us a time scale. But you have to know which crystallographic axes you are going through, which means you have to take another step and go to another instrument and get that orientation data, which is from an EBSD, which you guys actually have here, which is really cool. But if you're in a crunch, that's hard to have to send it to another lab and get that more data. If you have large grains and you can see their crystal shape, you can actually preferentially orient these grains, and so you know which axes it's on, meaning you can skip that step and just go straight to your diffusion chronometry. One of my supervisors and collaborators, Kendra Lynn and Lil DeSmither at HVO, developed this method and have a great paper that came out in 2023 about it. We've tested it with some other observatory scientists with other grains that maybe aren't from Hawaii or aren't as big or beautiful, and you still can use it. It takes a little bit more effort or a little bit more time to get your eye trained, but this is a super useful skill to help eliminate some of those extra steps. And then we put them into mounts. So you pick the grains, you put them into mounts, and then you can analyze them. So here is our SEM lab at HVO, and we look at imaging and BSE and chemical mapping, but we're also working on quantitative EDS. And so I don't know if that's something as familiar here, but typically when you want quantitative measurements of what you're getting from maybe your SEM, you have to actually take it to a probe, which is more expensive and can take more time. If you have an SEM, it's a bit more accessible. We're starting to develop, and a couple other places are doing this too, develop techniques to do EDS quantitative data on an SEM. And so working on this, it's really great to get those quantitative measurements. And these are types of imaging that you can get from the SEM and thinking about those textural relationships. So up here we have some crystal clusters of what's going on here, but here we have these really intergrown and radial looking textures. These are all from Mauna Loa. This is from my current research. And we know that something is happening synereptally with this to have these rapid nucleating spindles of crystals compared to these nice larger clusters here. And then over here we have some zoning going on. We have a resorption rim happening, so maybe there's some recharge happening or other things going on. So things that these SEM, these instruments can help us with. And then we have the WGS as well. The only thing is we only have one spectrometer, and so as opposed to a probe, you have 5 and can do quite a bit more quicker. Here we just have 1, but if we're just looking for eruption response and we just need to know the faux content of an olivine, super useful. And then this is what our EDXRF lab looks like, and we also have an FTIR to look at volatile measurements and gases within those grains. So that's kind of what we have as options when an eruption happens. This is our lab facilities between UHH and HVO. So now to the exciting part, let's talk about the eruption. So Kilauea erupted in the Middle East Rift Zone from September 19th to the 20th, out inside and near the Nepal crater. This is an image of day 2 of it, where we have, it started out here in this part of the eruption and then started reactivating fissures in the crater. For online here, we can say out here and then progressed inside the crater. And so we're going to go through the chronology and then the eruption response. To get you guys oriented, here is a schematic. I guess I'll use this. Schematic. We are looking north, so Hilo is up here. Kilauea Summit is here. We have the Halima'uma'u Reservoir and the South Caldera Reservoir directly beneath the summit. And then we have the East Rift Zone going out and the Southwest Rift Zone going to the left there. And to orient ourselves, this most recent eruption happens downrift of the summit in the Middle East Rift Zone near Nepal crater. So in the evening of the 15th and even before that into the 14th, we actually had a huge uptick in seismicity. This is a map showing the last month as of Thursday. So I think it's from September 2nd to October 2nd. This is all of the earthquakes that were happening on the island of Hawaii. On this map, the bright colored or warm colored dots are going to be shallow earthquakes, and the blue ones are deep earthquakes. These deep blue ones are South Pahala. These are deeper tectonic regional earthquakes and less to do with volcanic activity. But all of these red and orange ones are recent earthquakes that were happening in this lead up to an eruption. And here we can look at this cumulative earthquakes per day, starting from the 3rd and moving up until the 15th is, there we go, right there. And so clearly there is an uptick in seismicity. We're now in this kind of background of about less than 100 earthquakes per day is pretty standard. And prior to the eruption, we were reaching 500 earthquakes per day. There was a very clear increase. We knew something could be happening. However, this year, we've had quite a few intrusions that have been going on that have not led to an eruption. So we've had a really big uptick in seismicity, thinking there's magma movement going on, and then it finds a way to kind of re-equilibrate and redistribute, and an eruption doesn't happen. So leading up to this, we were like, is this another intrusion, or will this break through the surface? And in fact, it did around, I think, 10 p.m. on the night of the 15th is when the eruption started. But then if we want to look a bit closer, since that was the entirety of the island, this is now thinking specifically about the upper East Rift Zone and the Middle East Rift Zone. And these signals are very clear, and that ramp up right before the eruption becomes a very distinct signal that something may be occurring. There were also other data sets we were looking at. I didn't populate them here, but we were looking at tilt. So looking at the deformation, we have tilt meters where they we'll measure if the surface is moving and will tilt in a certain direction. And we get that measurement and you can tell if it's either inflation or deflation happening. And we were getting quite a bit of inflation prior to this as well. So another line of evidence of magma moving from the summit down the rift zone. So we kind of knew it was coming away from the summit and might be an east rift zone eruption that might be happening. So looking at the progression here, this is a map that we were able to make within the first day of the eruption. It started outside of the crater right here to the west of Nepal, and this line, the yellow line, is the fissure line, and the pink in that inset is actually the outline of the flow. This was done in the morning, got to go out on an overflight in a helicopter, and we have GIS mapping on board as well as a lot of photography and FLIR imaging, which is their thermal imaging, and we're able to actually map the lava flows without ever stepping foot on the ground because it's actually quite hazardous to get there. And so we were able to see this is where it was, and it started to calm down. This kind of happened overnight, and this is the FLIR imaging after going out on that overflight. We could see there was still some activity there, but not a ton. Going out that next morning, this is what some of those fissures still looked like. They were still degassing, but no red lava was coming out to the surface. The next day, so 2 days later, this map will stay the same until an updated map gets populated, but the dates are up here. So September 17th, it was reactivated in the energy of this eruption and actually continued to progress inside the crater. And so this is where fissures broke open inside and started flowing there. And this is what that kind of looked like on the surface. So we were able to go out again on a flight and actually start to get lava at the surface. And this is where that sampling video that you saw, this was from these activated fissures. So this was kind of our first way to get that quenched sample of the eruption and think about getting that chemistry and other aspects of the eruption. We'll just wait. The next day, it started to calm down again. So something about this eruption is it was not a consistent tempo, but it had these, you're kind of riding the wave of is it going off, is it waning down? And so this day there was, after the FLIR mapping, you could see there was still some activity in a tiny lava pond here, but majority in all the fissures were clearly like inactive and not quite, recharging. And we thought after about, a good amount of time, we're like, maybe this is the end. Maybe this is it. We don't know, but nothing's really going off again, and nothing's sending any more signals in other data sets as well. We were wrong. And actually, the next day, I think it was around 4 p.m., we were able, during this time, we go out and we don't just sample or don't just take pictures, but we also can set up other seismic nodes that are temporary or webcams. And so we were able to set up a webcam, very preferentially placed, I would say, and started to see a reactivation of this eruption and had lava falls, which was super cool to see. I had never seen an eruption like that. It was definitely really cool to witness. And so this was on the public webcam on HVO's website. Any of you could have been watching this. It updates every 10 minutes. Yeah, do you want to ask a question? Oh, amazing. Yeah, right? It's so cool. It's there. We are able to put out webcams as quickly as possible. So if something does happen, not only do we know that's going on, but the public has info on what's going on. And so this happened from about September 18th to 19th, this lava falls, which was a reactivated fissure outside of the crater and was so voluminous, it was pouring down into the crater. And so this is a couple time snaps throughout the night. It's a beautiful glow. And then the next morning, it was still going. So this was going for quite some time. And then we can only do overflights in daylight, so we had to wait until that next morning and hope it was still going, and was able to get a really cool imagery of what this eruption looked like and what these lava falls were. And also, this was still calming down. This was not its peak. So imagine kind of what it was that first day and overnight when we weren't able to go out there. And so at this stage, we were able to go out and get samples from this as well. And the question is, this was a different part of the eruption and was so much more voluminous and outpouring. Chemically, what was happening between the first kind of slow eruption that just kind of put out a little bit of volume and then compared to this, which was just this constant outpouring? Would they be chemically different? Did it get through maybe some previously stored magma that was colder and evolved, and now we're getting the recharge, and maybe this would be longer progressed. We didn't know until we get chemistry. So this is the benefit and kind of the need for this petrologic monitoring syneruptively, and that you can actually do something with petrology very quickly. And so that's kind of, this is now an updated map on the left here of the different lava flows as they continue to progress into the crater. This is a new FLIR map. So again, that's that thermal imaging. And we had that reactivated fissure outside of it and pouring into the crater. We're now filling majority of this. You can see different outburst flows that are happening and that are much hotter. And at the surface, this is kind of what that looks like. The upper left is that reactivated fissure that was happening outside of the crater, and then this picture was also one of those. And so we weren't having really tall fissures. A lot of times in Kilauea's really active history, these fissures can be like 100 meters high, and again, these were maybe like 10 or less. But still very beautiful and still very cool to be a part of and witness. And then the following day, this is now September 20th, we can see that the infilling has almost completely covered the crater floor, but we're no longer having these really high heat signals. And so again, we're thinking, okay, this is calming down. We're not having any active fissures that are hard to identify just with the eye, because you can't hike out to this area. You can, but it takes a long time. It's not like an easy access trail. I think it's a 12-mile hike to get there and back from this area. But also during an eruption, you're not just worried about where the next fissure is going to open up, you're also worried about wildfires. And this is a densely forested area, and so you don't want to get trapped out there. So that's why we were able to helicopter in, get our samples, deploy the seismic nodes, and deploy anything else we needed to make sure we were able to monitor it safely. And so this is kind of a near-end eruption photo where we can now see that I'll use this again. See the new flow that's covering the crater floor in this darker black color, and we have some degassing still happening, but no red lava. And actually this ended up being the end of the eruption. It ended on September 20th. Ended, I think, as at the observatory. We were like, we don't know, maybe it'll come back out, but it did seem that was kind of the end of the eruption. And this is just kind of a compiled view of what that looked like. So what did we actually do during this time? So a day-to-day, how quickly do things take? So if we take the September 17th is when it first started opening up in this fissure inside the crater. The new fissure opened up within the POW around 4 or 5 a.m. And we were able to get that data and know about it and start scheduling an overflight. And we were able to have people out there in the field by 7:30 a.m., which was kind of like first light able to get out there. This is where we were doing the water quench sampling, the imagery, the FLIR thermal mapping, as well as structure for motion, which is where you're taking a lot of photos. You can stitch it together and look at changes in the topography. We deployed seismic nodes and then set up those webcams. So those are the goals of the overflights where we're quickly going out. Within less than an hour, we were back from that. So it's really quick. You're going out, you're getting what you need, and then you're getting out of the field. So by 8:15, the overflight was finished. But now we have the problem where we are up in Kilauea, up in Volcano, and our lab is down in Hilo, an hour away. And so this is another kind of, maybe not issue, but point we need to take into account when we're thinking about eruption monitoring here. And so we needed to get the samples down to UHH. So luckily, some of the people who live up there were coming in for work, and we were able to communicate with our UHH collaborators and be like, can you bring those samples into the lab? So that was great. The samples got to the lab by 10 a.m. After that, we then needed to dry them. So that was our next limiting factor, is that the samples were soaking wet. And so one little hack was breaking off tiny portions, because for the EDXRF, you need only 10 grams of sample. So we broke up that piece that you saw in the previous picture. We're able to dry it within a few hours and start prepping it for EDXRF. At this point, we were able to get an actual chemistry, ran the analyses by 2 p.m. And we were able to see that the MgO content was about 5.9 weight percent. And it also comes with other major and trace elements that you can compare to other previous Kilauea eruptions. And we are also, with the MgO content, able to get a thermometer. And for comparison, previous eruptions in this area ranged between 5.5 and 10 weight percent MgO, 10 being a much more primitive, thinking mantle-derived magma, and in the 5s to low 6s is definitely an evolved, potentially previously stored magma. And so that was our first hint of what was coming out of this rift zone. Was the magma transfer coming from the summit and being this recharged magma, or was it kind of pushing out a previous magma there? And then by 3 p.m., we were able to actually pick through these grains and see what other phase assemblages there. Is there olivine to do other work on? And in fact, we did not find any olivine and only found shards of plagioclase. So once again, a very good chemical indicator of what type of magma is coming out. And so throughout this, between 7:30 a.m. to 2 p.m. was when we were able to go out into the field, collect samples, and get data back. And now all of this takes a lot of coordination and a lot of teamwork, and also the lab to be properly staffed. So sometimes people are on vacation. We actually had quite a few people out during this eruption, and we're able to do the best we could. And this is where we can rely on some of our collaborators in sending splits out. So this is where it really is a group team effort of figuring out what's going on with an eruption. But I thought it was quite impressive. This was the first time I got to experience this entire workflow of what it is to be out on an erupting volcano and get data back in that same day. And then as we continued to look through the chemistry, we could see those changes each day as it progressed. And as a little side note, this is happening pretty much at any eruption that we're doing. This is from the June 3rd, 2024 eruption in the Southwest Rift Zone. We were taking samples out there, collecting that data, drying it, and had it in the lab, and we're processing that same day. So this is something that we now have down as kind of our routine during eruption, and we have different shifts that are kind of set beforehand. We're like, you're gonna be in the field, you're gonna be in the lab, these are your roles for today. Okay, so now that's kind of the eruption chronology and what happened on a timeline, but research-wise, what does it mean? What did that MgO content mean? And so these are just, again, some really cool images while we were sampling. That's that reactivated fissure in the crater. And then this was on a solid lava flow that we also sampled to compare, but you can still see the glow underneath it, which was very cool. So getting into kind of the science here in background, we had seismicity propagating down from the summit to the Upper East Rift Zone and Middle East Rift Zone a couple days prior to the eruption, and definitely ramping up at the eruption time. Typical eruptions in this area within the 1960s and 70s were short-lived from 1 day to 2 weeks. So this was also a potential option where we knew this area could have these short-lived evolved eruptions. However, the most recent activity in this area was actually the longest eruption, I think the longest rift zone eruption at 35 years. And this is Pu'uo'o, and had some of the most voluminous eruption in the Hawaiian Islands here, or in the Big Island in recent history. And it was 4.4 cubic kilometers of material that came out in these 35 years. And for Hawaii, this was quite a bit. If we want to compare, Mount St. Helens 1980 eruption was under 1 cubic kilometer. And so thinking about how much lava was coming out during this eruption. And this ended in 2018, so not that long ago. So another kind of thought at the observatory while we were seeing the seismicity go into the Middle East Rift Zone in the similar area, are we starting into a new Pu'uo'o era? Like, is that happening next? And again, this is where this chemistry and active monitoring that's happening is really important, as well as getting time series data, so time series samples. Here is a map area of the Pu'uo'o. We have Nepal Crater to the left. This is, again, the summit. Halema'uma'u is right here. And Nepal, where the eruption happened in September, is to the left of this. And this is all of Pu'uo'o's eruptive products. And it went all the way down into the ocean and crossed highways. And so this is why this is definitely a hazard here in going near communities and roadways. So prior to Pu'uo'o in 1977 to 83, the East Rift Zone eruptions contained stored magmas for decades that were more evolved. And so this was crustal stored magma flushed out through the conduit and replaced by mantle-derived magma later on. And so the first phases of Pu'uo'o were also evolved and previously stored and mixed. So how did our chemistry compare? So looking at this, we're going to do just a bit of geochemistry. So hopefully that's okay. We have magnesium here on the x-axis, going from 10 weight percent on the right to about 6 on the left. And roughly how you can think about this is more primitive to more evolved. And then on this other, we're looking at trace elements of, again, nickel and chromium. If we're wanting to just think about how primitive or mantle-derived something is, nickel and chromium are more enriched in those more primitive samples. And in this case here, the triangles, so the purple triangles, as well as the other ones, are evolved and mixed samples from early episodes of Pu'uo'o's era. And so this is where all the triangles are. They're on that more evolved low MgO content, and this is where the rest of that more voluminous activity was. And this is where it matters where our data plotted. So the September 2024 eruption is now in the gray boxes, and it had, you know, a decent amount of spread within calcium. Not that much, we're looking at less than 1 weight percent, but a little bit of a spread. But again, this is rapid EDXRF. We then take those samples later and run them under more quantitative WDXRF to kind of back it up. But for eruption response, this gave us an idea that we weren't having high MgO basalts coming out. We were actually having this evolved, slightly mixed, colder evolved magma that was being kind of pushed out. Which gave us kind of the idea that maybe this isn't going to be such a long-lived eruption. Maybe we can prep for that. But then, after, this is the importance of the time series, because then we had that outpouring. And the question was, what composition was that? Did we already blow through that stored magma and now we're getting the recharge that came from the summit? And it ended up being the exact same. It plots within that gray box. So it stayed evolved. It stayed the entire time, pretty homogeneous at a bulk rock chemistry level. And so it seemed that this was pretty safe to say this might be a more evolved and relatively short term, and then it ended up being that case. Obviously, if things continued, they can change so quickly. It could have gone through that evolved stored magma and then did get the recharge to the surface. And if that would have happened, we would have been prepared, but continuing to sample and monitor that. And so this is kind of why it's so important to have this interplay between real-time monitoring versus research questions. And so this is, I kind of just said that. But something to note here is that there have been 8 eruptions between Kilauea and Mauna Loa in the last 4 years. So that's looking at an eruption almost every 6 months, which means we're not just thinking about monitoring syneruptively, but we're also trying to prep what might happen in 6 months. So even if things aren't getting done the week that the eruption is happening, that next stages of taking this data and taking these samples is important to understand them, because it might be helpful or insightful towards an eruption that's happening in a few months. So thinking about how long the magma was stored there and was it thermally sustained, why did we get that magma out? And so this is where those crystal records come back into play. It was a relatively crystal poor eruption, but we did have large plagioclase phenocryst. And as of right now, we are picking through them, and my colleague, Drew Downs, is actually making a mount of these plagioclase and then sending them to me right now so I can analyze them and look at diffusion chronometry on these plage to think about how quickly were they reheated to eruption. And so we know, were they thermally stored there and ready to erupt for the past, decade, or were they just recently heated a couple months ago? So these are kind of questions we get to ask here. And the tension between syneruptive monitoring, long-term monitoring, and then your research questions. So these are all things you get to balance at an observatory, not just doing research and not just doing operations. So that's kind of the summary of the eruption response and chronology. And the next part of the talk is actually going to be kind of about my career path and how I got here, because that was kind of an interest of how do we get to this position and how do you do that. And so some of this will be a little bit repetitive. Hannah mentioned some of it, but I did a BA at Willamette University in Salem, Oregon in environmental science, and I actually was a non-geo major to start. I wanted to do psychology. And then I took a natural disasters class and thought volcanoes were super cool. And that whole thing of this micron scale changes having big implications toward these natural features just caught me. But I didn't want to leave Willamette, and because I was playing softball there and I wanted to stay at this small school. And so I switched my major to environmental science, but still was not geology. And so I made my way to make that better, and I did independent study courses where I taught myself mineralogy and some other petrology things, and then I studied abroad and took my first official volcanology course at the University of Canterbury in New Zealand. I got to spend 6 months there and take actual coursework in geology, and that's when I knew I made the right choice. This is what I need to do. How do I keep going? How do I keep getting to where I need to go? And so I luckily had a lot of great mentors at my undergrad institution, and they were able to let me know about NSF REUs. So this is a research experience for undergrads. It's really great if any of you are still undergrad here and are looking into that, getting research experience. They have a lot of them. Mine was based at Vanderbilt University, and I got to work with a lot of great scientists. This is where I actually did a ton of field work. And got to go to Vanderbilt and use their lab, and this was my first time really working with chemical data. In this time I was going through my undergrad, I was also cold emailing everyone I could. So I emailed OSU, which was a nearby university that I knew had a geology program, and I just emailed professors, hello, I'm ready to work. Do you need a field or lab assistant? And that actually worked really well. I got multiple positive feedback. I was a lab assistant for a couple different grad students, and I was a field assistant for 2 different PhD and master's students. And I got to learn so much in those opportunities, and I got to work in labs and really figure out what direction I liked. And so even if you're not totally where you want to be, just email people, reach out and figure that out. And it's just as important to figure out what you don't like. So after this, I kind of knew I wanted to do volcanology and igneous petrology, but I couldn't go to grad school yet because I didn't have the right degree and I was missing a couple official courses. So I did a post-baccalaureate year at OSU and got to take a lot of great classes and officially do some more field work. But I also ended up working in the Argon Geochronology Lab, which was also really great to learn those skill sets and work in that type of lab. It's where I learned a lot of those base skills that I now use every day. And then from there, applied for grad schools and didn't really think I wanted to do a PhD. I wanted to get a job and go work. And that's funny because I ended up staying for 7 years and I did a full master's project and then defended that and then started a PhD at UNR as well. And this was such a great time at this grad institution. I had really great projects and advisors there and got some really great research opportunities. And this is all of my fieldwork was in Chile, both for my master's and my PhD on different volcanoes. I was out there probably 4 or 5 times. I also got to do some really cool helicopter work in my PhD. But I also, because of that connection back to OSU, I was going to OSU to do some probe work for my PhD and talked to the lab manager, just was catching up, and he was like, we actually need another grad student on this research cruise. Can you go on it? And it's like paid for, and you just have to do science on a ship for 7 weeks. And I was like, that sounds great, yes I can. And so because of these connections that you're making throughout time, you get to keep those connections going. I got to go on the Nathaniel B. Palmer here for 7 weeks in the South Atlantic Ocean, working on underwater volcanoes at the Rio Grande Rise. We got to map new seamounts that hadn't been mapped before and dredge up rocks from the ocean floor. It's a really great experience, and some research projects kind of came out of that. After finishing my PhD, I applied for a lot of different things, one of which was the NSF intern at CVO. And so the NSF intern is a great program. It has to be while you're in your PhD, and you also have to be under an NSF grant. But if you satisfy those, you can apply to work at somewhere that's not an academic institution. So this can be at national labs, this can be at USGS, at volcano observatories, wherever you're interested in. The whole point is to get you non-academic experience. And so I knew my goal was to work at an observatory. I wanted that. So I was like, let's go to CVO. I cold emailed someone and said, I want to start a project. These are my skill sets. Do you have these? Or I can make up a project. Let's work through this. Was able to develop that and write a proposal, and it got funded. So I was able to go to CVO for 6 months. The great thing about these is that they are 6 months funded, and you can also extend them for a full year. I only did 6 months because at this time I had also accepted my position currently, which I'm now at HVO as a Mendenhall postdoc fellow, which is honestly just a dream position. I'm very excited to be here working on Mauna Loa and doing igneous petrology at HVO and being at active eruptions. It's a very unique opportunity. And so this is kind of the pathway, and I guess the takeaway is that non-traditional paths are great. You don't have to have always the exact background you think you need, but you need to start accumulating the skills that you think you might need or think might be helpful, and emailing people and reaching out and applying for everything you can. And all of those experiences will help you later on. Like I have so many connections still from back in 2015 in my undergrad that I'm still working with. So this was a really interesting pathway, but it's exciting to be here. And because field photos are cool, here are just some of my experiences that I've had between all of my research experiences. So this upper picture is when I was on the ship and we were using the dredge, and I was on the night shift. So this was probably around 2 a.m. And I was dredging up rocks, and there's a view of the middle of the ocean. Most recently here, this is during the June eruption, and I was using a laser rangefinder to measure the fissure fountain heights as well as the length of the fissure during the job. This is from my PhD in Chile. This is Puyehue, Estratocone, and Cordon Cauye, which erupted in 2011 and 12 and is still showing unrest. And this is also from the Andes, looking at tephra sections. And then also we do lab work. So there's also some windowless building time. As extravagant as it is, you also do quite a bit of lab work. Let me see. Well, we're kind of right at an hour. So this is kind of the end. I am currently working on Mauna Loa and looking at the crystal cargo mineral chemistry, looking at, we don't really have a good understanding of what's going on underneath the surface or any real mineral chemistry. And so that's what I'm focusing on. If you want to talk about that after, I'd be happy to, or show you some data. But in general, this has been a really great opportunity, and I'm excited to share with you kind of different career paths and opportunities you can get into. So yeah, thank you.
Thank you for a great talk, Heather. We're going to do a little bit of Q&A. If you have a 1 o'clock gig or something, a field trip's about to leave, if you guys can just slip out quietly. But let's do Q&A for another 5 or even 10 minutes perhaps. And Heather will remember to repeat your question so that the home crowd can hear. Questions, please.
Yes.
You've got this eruption starting up, and then you go make standard measurements. Does in practice, you see a bunch of stuff, like, oh, we need to stop doing what we were going to do and go do something else. Does that happen in practice?
Okay, so the great question. The question was, as we're collecting real-time data, does that change our plan day to day as an ongoing eruption response? And so I've only been there for a little bit, so my experience is limited. But I think there is a typical plan that is happening that we know if an eruption continues, we're going to try and go out and sample that. We're continuing to look at the seismicity. But on the whole, yes, we want to know what's going on. And so if the chemistry was changing or if we knew a new outburst flow, we would be like, well, we know the chemistry here, but now we're outpouring different data. This might be different. We should probably go check that out. So I think it does impact it. There's a base level that we are, I think, always going to do because you just want to monitor and have those time series collection of the eruption response. But I think it kind of is honestly eruption dependent and might change. So. Yeah. Yes.
Can you talk about what kind of timescales that's applicable for? Tens of years, thousands, or millions, or anything like that?
Yeah. So the question is looking at the diffusion chronometry, what are the timescales I'm looking at? It's actually quite short, especially for Hawaii. So in olivines, I have a couple slides later on, but there's really cool data sets where in the olivine diffusion, modeling that zoning prior to an eruption, it's on the order of like 2 months that we're seeing a change happening. And Kendra Lin has actually a couple papers coming out, and she's done really great work of compiling that with our other monitoring data, so the seismic and the tilt and the GPS information. And a lot of these spikes that are happening prior to an eruption are also happening at the 2-month mark. And so we're actually seeing these recorded in the mineral chemistry, and they're showing us that that diffusion and that change in the environment was happening on a 2-month scale, and we're actually seeing that reflected in the surficial data sets. So typically for Kilauea, the olivines, they are shorter lived. I envision that the plagioclase that we saw from this eruption will have slightly different because it was so evolved, it might have been there for a while, and Pu'u'o was erupting since the 80s. How long was that part of the rift zone active? It might show, on the order of decades or years, but we don't know yet. But so typically things are pretty quick and happening very fast at Hawaii. So yeah, thank you. Yes.
So you mentioned using, as I understood, fluid inclusions for barometry?
Yes.
I'm familiar with thermometry, but
Yes.
how do you do it for barometry?
So it is looking at kind of where it traps the gases, and specifically the CO2, and that it acts as like a pressure capsule. And so you're able to look at the pressure, and as it gets trapped inside the mineral, it does not change as it ascends to the surface. And so we get to actually tap into what pressure that was trapped at prior to eruption. And with melt inclusions, with bubbles, you use an FTIR to look at the volatile content within the melt inclusion, and a Raman to actually look, and this is like infrared spectroscopy that you're looking at, to look at the CO2 content and the mass and densities in it, and that can be equated to the pressure or depth. And so the same with fluid inclusions, as they are just bubbles, we can look at the CO2 and the density and figure out what the pressure was associated with that density. And so they're really great tools, and it can be really fast. Also, the prep work for fluid inclusions is much shorter and easier than melt inclusion prep.
One more?
Yes.
So I saw the pictures of like the outfits that you guys use when you're out in the field collecting these lava samples. What other safety precautions do you guys have in place to keep volcanologists protected?
Oh, plenty.
Could you repeat that question?
Oh,
please?
yes, thank you. So the question was, what type of safety gear do we wear in the field to make sure that we are safe during eruptions and during sampling? And so at pretty much all times, anytime we're out for eruption response or field work, we have a bag full of things, and that is, we have hard hats to protect if anything's flying. We have gas masks that are always with us. We also have an SO2 monitor badge, so you might not need your gas mask, or you have it hanging and you're doing something. It will beep if it gets to a certain level where it's like you need to actually put on your gas mask and be safe. So we have that. We also always have inReach and satellite phones. The field gear that we're supposed to wear is mostly cotton because you're near things that are really hot, and so if you're wearing synthetic material, it can melt to your skin as opposed to just burn. So all of the field gear is cotton, and then when we're flying, we have flight suits as well, and there can't be anything loose. Everything has to be very contained, and we also have flight helmets. And I'm sure I'm missing some things, but that's kind of the gist, that we are having hard hats, gas masks, gas badges, and proper protectant. And then when we're lava sampling, actually, there's an extra layer of, you see the silver suits that are heat resistant and give you an extra buffer, and then we have a face shield to help because it is really hot getting close to it. And so you want to make sure all of your skin is not exposed. So, yeah.
Let's thank Heather one more time. What a great talk.
Awesome.
Come on up, talk to the speaker if you like. Thanks for coming. We'll see you next Friday.
Can I take this off?
Sure.
Okay. Thank you so much.
You did great.
Oh, thank you. Hopefully it was great.
Superstar.
Awesome. Yeah, here you go. I appreciate it.
Thank you, Heather. There's your adoring fan.
Oh, thank you.
I'll be with you all in a second.
Yeah, we're gonna work.
Glad you came to this, man. Hey, man. Okay, everybody, let me swing the camera around and we'll say a couple final words here. Jordan Carey. Well, we're back in the saddle. Can I test something with you quick before we say goodbye? So I've got the speaker off now, and I've got both of these Rode mics going right now. So one was the speaker mic and one is the mic that I'm using right now. I'm just going to talk for a couple more minutes with both on, and then I'm going to turn one of these off and see if there's any difference. So, and I think I'm pleased enough with these Rode mics that I'm going to buy 4 more of these things for the field. I think I'm going to get off of those ceremonic things and other things. So Nat's got me excited about these Rode mics. So I'm just now starting to learn about the possibilities with these guys. So what am I doing? I think I'm just going to, so I have 2 mics going now, and I'm going to turn one off and see if there's any change. Okay, so 2 mics, you've heard 2 mics for a while now. Oh shit, okay. So now now it's red, so I think now it's recording. Okay, I'm doing this for Nat more than anything else. Nat, you're watching the replay of this thing. Now that the red light is on, does that mean that I'm now recording into this unit as well? Or maybe somebody at home knows? I guess the blue light it worked today, right? So she just had the blue light on. So the blue means that we're communicating with the receiver, I think. I thought I was turning this off, but I guess I'm turning now on whatever. Okay, I'm turning. Now I'm back to blue only. I assume you can't hear any difference, and now I'm going to turn this frickin' thing off. Okay, so now this thing's off, and I'm curious if this sounds any different to you now that I'm down to 1. I don't think it will, but I'm just curious. So I'll stick around. There's delay in the live chat, but I'm just asking if you hear any difference with just me doing 1 as opposed to 2 mics. No change? Yeah, I guess I'll put my headphones on when I watch the replay and make sure that I know what's going on. Exactly the same. Yeah, thank you. I'm very pleased. There were enough moving parts that I wasn't sure how this was going to go, but unless I am very upset by watching the replay, it sure seemed like that worked really well. And Hannah brings in these outstanding speakers. They're basically friends of hers, but they are all outstanding. So I really enjoyed that talk, and I hope that you did too. Okay, everybody, thank you very much. I love you, and we'll see you next Friday for another talk. Can't remember, but it's one of Susan Kaspari's Italian colleagues who will be speaking. Thank you, I love you, and goodbye from Ellensburg, Washington, USA.